To your second semester review. All right, welcome to your second semester review. Clarify, and couple people asked if this is like from whole year or just a semester. It's just this semester, so no trig, sine, cosine, tangent, none of that stuff is on this test. Most of this test, big topics, factoring and polynomials, all of that stuff. We got some logarithms. We have some sequences and series, and then we got our conic sections, some basic graphs that we did. Those are our big topics that we went over this semester. So if we start on the front page, 1 through 10 is really all about polynomials and factoring and foiling and setting stuff equal to 0 and getting all those different pieces. And so basic one would be like number 1. It says approximate the real 0. That also means like an x-intercept. That's what it means. Roots, x-intercept, zeros, they all mean the same thing. And approximate the minimum and maximum to the nearest tenth, so 1 decimal place. So this is a calculator problem. And we know, because we've used this menu a lot, that if we go to our calculator and we do second trace, there's all of those options for finding a 0, your x-intercept, finding your max, finding the min. And if you do put this on your calculator, you got to do zoom 6 to see it. Make sure you're in the 10 by 10. And it kind of looks something like this. I know it's me doing a really horrible drawing. But we see that I do have an x-intercept. No, that's not where it is. That's where it is. You have a minimum and you got a maximum. Okay. And so what you will have to do is when you choose those different options, you got to do left bound, right bound. For the 0 left bound, if I go to the left, I'm above the line. If I go to the right, I'm below the line. So that's how I do left bound, right bound. For the minimum and maximum, it's easier. Left bound, right bound, left bound, right bound. We got those pieces. But when you do that on your calculator, we need points. And when all is said and done, the minimum, maybe, spoiler alert, answers are coming, but try it on your calculator. -4, -5 for the minimum. Maximum is -2, -1, 0, -5.1, comma 0. That one didn't round off to a whole number, so we do it that way. So you can find your x-intercepts by graphing, your x-intercepts, your roots, your zeros, whatever you're calling them, but there are some ways to do it that makes it a little bit easier, especially if you want the exact, like you want a whole number, or maybe you want the square root, because square roots are more exact than decimals. One of those methods, best methods, would be factoring, if you can. We could try factoring. That's what we're going to do on numbers 2 and 3. And so I know number 4 is kind of blocking it on the screen, but I'll write it out. I may erase some work, and then we're right over the top. We'll make this work. So if we can find all the roots, if we can factor, that is the desired method to do it because it's the easiest, and we're good at factoring. That number 2, I have 3 terms. Highest term has an x squared. Number in front of that is a 1. So I'm looking for 2 numbers that multiply to a +6 that add to a -5. Do not jump on the 6 and the 1. They won't get you the +6. If I need double positives and then a negative that it adds to, I need double negatives. And so if I set these pieces equal to 0 and solve, that becomes a +2 because I would have to add the 2 over. And the x minus 3 equals 0 would become x equals +3. And I have 2 answers. We know we're supposed to because that highest exponent is a 2. I got those. You could see that on a calculator because it doesn't specify how to do this. 2 and 3 say find all roots. 5 through 8, you have to factor. You got to show it by factoring. But number 3, I have 3 terms. There's not an x squared in front, but we can make one to be in front. If we just factor out an x, we're going to GCF out the x. Let me erase my little doodle over here. And the x that's out front, it's not going anywhere. In fact, if I set that piece equal to 0, one of my 3 answers, one of my 3 roots is 0. I have to have 3 because I have an exponent of 3. But the rest of it, we can factor this now. 2 numbers that multiply to a -3 that add to a +2. We're going to go +3, -1. And so along with the x equals 0, I'm going to have x equals -3 and x equals a positive 1. If I set those chunks equal to 0 and solve, those are my 3 answers that I get. If you want to make sure you're right, if you can FOIL all your stuff back together, if you factored it, you should get back to the original one. We got our 3 answers. You could always double check on the calculator, but when you get down to 5 through 8, they may be imaginary, they may be square roots or fractions, and you can't see them exactly as whole numbers, so just got to be careful. Alright, and number 4, we have a huge polynomial, 5 terms, x to the 4th, then cubed, then squared, then x, and a constant, all these things. And it says write it in factored form. One of them's been given. So when we get our answer, when we get all of those factors, one of them is that x plus 5. It'll be in my answer. But I have to know all of the other factors, and this is where we run into a problem, is because I don't have any method of factoring 5 terms. I can do 4. We can factor 4 or we group it together. I can factor 3, I can even factor 2 maybe, but I can't factor 5. So we have to somehow make this polynomial smaller. And it says one of the factors has been given, and we know factors divide out evenly. So if I can divide out the x plus 5, then I can factor what's left over. And the way we're going to do that, easiest way, is synthetic division. You guys may say, that sounds familiar, I can't quite remember it. We're going to just take all of the coefficients, so 1, 7, 8, -14, and -20. And I need not the factor, not the plus 5, but the piece I have to divide out is the root. I have to take out that -5. So we're going to always, whatever they give us the factor, we're going to swap the sign. So if it had said x equals -5, then I would take a positive 5 and put it on the outside. But it says positive, so I got to take negative. And what we do is when we use synthetic division, it's just the coefficients. We bring down numbers, we multiply, and fill in all the commas. So I'm going to bring down the 1, and I'm going to multiply -5, add them together, positive 2. Multiply, add together, multiply, add together, multiply, add together. Great, we got a 0 at the end. That's my remainder. So what's left over, I started with 4, or x to the 4th, and I took out 1, so I have an x cubed, 2x squares, -2 x's, and a -4, a -4. But I'm not done. I took one of them out, and the reason why we do that is because I can factor what's left over. I can make this smaller and factor by grouping, where we group first 2, last 2, and we take out greatest common factors. Like out of the first group, I'm going to take out an x squared, and it looks like I get an x plus 2 left over. So I have to make this x plus 2 show up again for factoring by grouping to work. So in order for me to do that, if I take out a -2, then I have an x plus 2 left over. So along with this x plus 5 that's up here, I'm also going to have an x plus 2. And if you guessed x squared minus 2 is your other factor, you are correct. That is factored form. Now I know some people will think, well, you can factor this down, and no, I can't. This is not perfect squares. So I can't factor this anymore. If it was perfect squares, like x squared minus 4, then I could do x plus 2, x minus 2. But 2 is not a perfect square, so I just leave it. But looks like I'm good to go. I started with an x to the 4th, and I have 2, 3, 4 x's total, so they are all there. I got my factors, x plus 5, x plus 2, x squared minus 2. 5 through 8 will kind of describe all the different types of factoring methods that we've talked about. Number 5 is kind of similar to what we just did, factoring by grouping. We have 4 terms. So finding all the zeros by factoring, I got to factor, set the pieces equal to 0, and figure out where are these x-intercepts. They could be whole numbers, they could be square roots, they could be imaginary, they could be fractions, they can be anything. But we have to make sure that on number 5 I have 3, 7 and 8 I got 2, and on number 6 I have 4 answers. So we will do it piece by piece. Number 5, we're going to group first 2, last 2. Out of the first chunk, I can take out an x squared, and I'm left with an x minus 3. And to make that x minus 3 show up again, I have to take out a positive 4, and so I have it. So my two factors, x squared plus 4 and x minus 3. And I got to set these equal to 0 and solve. The first one's not terrible. X minus 3, I got x equals a positive 3 when I move it over to get x by itself. And x squared plus 4, we know how to do this. The first thing to get the x by itself is subtract the 4. And the next thing to do would be to take a square root to get rid of the x squared. Now a few things have to show up when you personally have just drawn on a square root. One thing, plus or minus, has to show up. That's how we get 2. And also, if it was a positive 4, I would just say plus or minus 2. But this is a negative 4, and we are usually not allowed to take square roots of negatives. To bring that out, we have to toss in an I. So if we get I square root of 4, I really know this is plus or minus 2I. So the square root of positive 4 is just plus or minus 2. The square root of negative 4 is plus or minus 2I. There's 2 answers. And I got my third one over here. We are all set up and good to go. Just remember, square roots of negatives doesn't mean it's impossible. It's just an imaginary number. You would not see those 2 answers on the graphing calculator. You would only see one of them, only the positive 3. Number 6, it has 3 terms, and that number in front is a 1. I'm not going to panic that it's an x to the 4th, because instead of just x and x in my pieces, I'm going to use x squared and x squared. And so if I need 2 numbers that multiply to a negative 42 that add to a negative 1, I would use the 2 numbers negative 7 and positive 6. I would use those pieces. If I need to set these equal to 0 and solve, follow me down here. X squared minus 7 equals 0. I'm going to add the 7 to the other side, and I'm going to take a square root, which means plus or minus. I get x equals plus or minus the square root of 7. And that just stays. 7's not a perfect square. No perfect squares are inside of it. We just have to leave it. And if I do the same thing with this x squared plus 6, I got to set it equal to 0. I'm going to move the 6 to the other side by subtracting it, and I'm going to take a square root. Few things have to happen. I have to have a plus or minus. It's got to show up. This little negative cannot be on the inside, so I need to bump it to the outside as an I. And 6 is also not a perfect square with no perfect squares inside of it as a factor, so we leave it as the square root of 6. I do have my 4 answers. Positive square root of 7, negative square root of 7, positive I square root 6, negative I square root 6. Don't be afraid of solving these little equations. These are just teeny tiny. Get the x by itself. You guys can do this. Alright, number 7 is probably our easiest factoring. It's difference of perfect squares. There's a rule for it. If I have 2 perfect squares that are being subtracted, then I take what's making them a perfect square and I do one that says positive and one that is a negative. You have to have 2 pieces. You have to have 2 pieces. You can't just take the square root and say x minus 4. No, you got to have 2. So I'm going to take x minus 4 is one of the pieces, but I also have to have an x plus 4, both of those. When I set them equal to 0 and solve, I get a positive 4 and I get a negative 4. There are my 2 answers. Pretty plain and simple with difference of perfect squares. You got your little fancy rule right here. In this last option, 3x squared minus 7x plus 4. 3 terms, no GCFs, number in front is not a 1, so we are going to slide the 3 back and use slide and divide. So x squared minus 7x plus 12. Now I can factor it. 2 numbers that would multiply to a positive 12 that would add to a negative 7. We got negative 3 and negative 4, double negatives. And we're going to divide by the number that we slid over. That would be the 3. So one of my pieces, and again, follow my arrows, one of my pieces will be an x minus 1, where the 3 simplify, so one of my answers, x equals 1. And my other one, the 3 and the 4, they do not simplify, so we need to tuck the 3 in front of that x, so I get 3x minus 4 equals 0, and my other answer would be 4/3. Add the 4 and divide by 3. So we have both of those answers. We got 2. We should have had 2. Don't forget to divide after you slide the number over. But we have all of these different types of factoring. We had factoring by grouping for number 5. We had the easy factoring on number 4. We had difference of squares on 7, and we had slide and divide on number 8. If you're thinking about, tips to put on a cheat sheet or little tips and tricks, maybe kind of jot down the different types. 4 terms, that's grouping. 2 terms, that's usually difference of squares. Number in front's not a 1. Slide and divide, little things like that. It's up to you what to write, but trying to give you tips along the way. Number 9 and 10. These have very fancy instructions. Write a polynomial function of least degree with integral coefficients that have the given zeros. Basically, blah, blah, blah. These are the answers. We need to know what was the polynomial, what was that equation first. We're kind of doing the opposite of all of this factoring stuff. On number 8, we went from the equation to all the little pieces. In number 9 and 10, we have all of the little pieces, and we got to get the equation. So what it means is they're saying I had an answer that was a -1 after I set all of these equal to 0 and I solved for it. I had all of these answers. But we have to go backwards now. That I don't want the -1 to be on the right-hand side. I need to make sure it's back on the other side. Okay? I don't want the positive 3i on the right-hand side. I need to move it back over to that side as well. Let me change this real quick. Okay, that's a little easier to see. So we have our factors, what we would have split this all down into when we were factoring it. But now we need to FOIL it all back together. So we can pick any 2. I'm going to be smart and pick the 2 with the i's. So if we go first, I get an x squared, outside, positive 3ix, inside, negative 3ix, and then negative 9i squared. So it looks crazy, but it's actually pretty convenient because the middle 2 terms are gone. They're out of there. And we had this rule that said I squared is a -1. So this is really not -9 times I squared. This is -9 times a -1. So we get X squared plus 9. And this little x plus 1 is still here. So now it's a lot nicer. Now it's just, I got to FOIL one more time, and we'll have all the pieces. X cubed plus 9x plus x squared plus 9. And this is technically the correct answer. There's nothing wrong with this, except it's not in nice, neat, descending order. So if we flip-flop those inside 2 pieces, we'll get it in nice, neat order. We got all the way back. X cubed plus x squared plus 9x plus 9. If we had factored all of this down and set it equal to 0, we would get all of those pieces up here. But we went backwards. That's what 9 and 10 are asking you to do. Number 10 is going to work the same way. It just doesn't have i's. That it had an answer of x equals 3, x equals -5, and x equals positive 1. So when we made these factors, I would have to subtract the 3 back over, and I would have had an x minus 3. I don't want the numbers on the right-hand side. I want to put them back to get the factor, so I would have to add the 5. I'm going to kind of undo everything, and I would have to subtract the 1. So if we do this, we can do it anyway. We can just group 2 of them together to multiply. I'm going to do first, outside, inside, last. And it doesn't quite go away, add to 0 like the other one did, but at least I can combine the middle 2 pieces to x squared plus 4x minus 5. And I got to bring down this x minus 3. So we have to keep combining, keep going. It's a little bit different than just FOILing when you have 2 terms times 3 terms. That just means this x has to go to all 3 pieces, and we get x cubed plus 4x squared minus 5x. And this negative 3 has to go to all pieces. Negative 3x squared minus 12x plus 15. And we combine any like terms that we see. I don't see anything else with the x cubed. I see a positive 4 and a minus 3x squared, so we have 1x squared. I see negative 5x's minus 12 more, so there's negative 17x. And I got plus 15 on the back by itself. So if it looks crazy, polynomial function of least degree, blah, 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 you got to make sure that if you start with the answers, you got to FOIL it all back together to make the equations. So the front page is all of your factoring and FOILing and setting stuff equal to 0 to get those x-intercepts. The next page changes just a little bit, because the next page, 11 through 23, is our logarithm exponential stuff. Now, we're not panicking because we see logarithms. We've talked about all year that logarithms are just a different way to write something that has an exponent, something that's an exponential. That's what we're looking at. So somewhere on this review, on your cheat sheet, I need you to write these three things that are at the top. That anytime we're trying to condense or expand these logarithms like 11 through 14, take 2 or 3 logarithms into one, or take one logarithm and split it all apart to little teeny logarithms, that we have to know these things. If I see anything that's being added, I know that's multiplication, or vice versa. If I see something that's being multiplied, I know to split it up, I got to add them. Subtraction, not substitution, subtraction and division go together, and anytime you see coefficients, they were exponents, and if you see exponents, they got to become coefficients. They got to become the numbers in front. And so when we see problems like 11 and 12, this is, instead of writing 2 different log 7s or 2 different log 5s, I need to combine them together to make one log 7 and one log 5. So the first thing that I notice in number 11 is that I have some coefficients, so I need to bump them back because they were really exponents to begin with. Sorry, can't talk. This is a to the 5th. This is b to the 6th. So now I moved them back. We got that one rule taken care of. But something else that we also see is it looks like they're being added together. Well, to make it one logarithm, addition is really multiplication. So we're going to take this, and inside this log 7, we're going to multiply. Okay, sorry, I had to pause. They made a really loud announcement. But anyways, we're going to multiply them together. So instead of saying a to the 5th, b to the 6th, we're going to multiply them, and we have one log base 7 now. And we're going to do the same thing with number 12. I see some coefficients. They got to get bumped back. So I have log 5 of a to the 10th minus log 5 of b to the 5th. And we just want one log base 5. But subtraction is division. So that's how we're going to have to write it. Log 5 of a to the 10th over b to the 5th. We smash it back together. It makes it a lot easier than having all of those pieces. And so with 13 and 14, we're basically going to go exactly backwards. Instead of having the coefficients and the pluses and the minuses, we have the multiplication, and we got to get to the pluses and minuses. Because on like 13, I see a lot of stuff that's being multiplied. And if I wanted to spread this apart into a lot of different log 6s instead of just one gigantic one, I would have to add all of these log 6s and all of these different variables, the letters, together. So we split them all apart. There's only one little thing, that this little guy's got to jump to the front. So we have log base 6 of u plus log 6 of v plus 5 log 6 of w. And we basically popped it all out, undone it all, to make it look like problems like 11 and 12. We're expanding it into many logarithms. Same thing with 14. I'm going to I see division, and I'm going to change it to subtraction. So I'll write it down here. I got log base 8 of u to the 6th minus log base 8 of v to the 6th. But any exponents have to come to the front to be coefficients. It's just proper math, and we're going to be super proper on all of this. So 6 log 8u minus 6 log 8v. And condensing and expanding. If I was taking this test, I would have those little tips that adding and multiplying are the same, subtraction, division, coefficients, and exponents. I would have that along with some tips on how we solve the equations that are coming up. Alright, and to wrap up this video, I'm going to wrap up this one on 15 and 16 because even though one's a log and one's natural log, the way you solve them is basically the same thing. There's lots of different ways that we can solve all of these different equations, and we got to know them. We got to have different tips. The easiest two are 15 and 16. These are the easiest two, because what they're saying is I have same base equal a same base. And this is awesome, because really, if this log 16 of all of this junk is the exact same thing as the log 16 of this little piece, well, the log 16s are already the same. These pieces must be the same. They have to be equal. If the left-hand side equals the right-hand side, then all of the pieces have to be the same. And so that's what it means. If you have same base equals same base, then what we do, we take the inside pieces. I just drop the bases off, and I take this piece. So I have a lot of negative n's. I'm going to add 2n to the other side. 2n. So I get negative 6. It's gone on the left-hand side. Negative 1 plus 2, well, that's just 1, so it looks like n equals negative 6. And if you wanted to see if you got it right, if you plug in a negative 6 here and solve it, looks like we'd get a positive 12 minus 6 is 6. If you take a negative 6 and plug it in here, a negative 6 is a positive 6. Both sides do equal, so we did it right. We did it correctly. That's what we're going to do for number 16 as well. I don't care that it's a natural log. Base e's, I don't care. This natural log of this chunk equals the natural log of this chunk. So the chunks must equal each other. The only thing that's a little bit different about this one is now you got an x squared. But x squareds are very, very, very important. When we see squares, we know that that usually means that you're probably going to have to factor, because two answers are going to have to pop out. So we're going to move everything from the left-hand side over. So we get 0 equals x squared minus 3x minus 10. So we can factor two numbers that multiply to a negative 10 that add to a negative 3. How about negative 5 and positive 2? We set them equal to each other. Positive 5, negative 2. Or sorry, not equal to each other. We set them equal to 0. And we solve. So we get two answers. And if you want to try it, plug them into both sides and see if the inside parts equal to each other. You got to check that out. But we have an x squared. We got our two answers. So we are good to go. Same base equals same side. We drop the base. Sorry, same base equals same base. I was morphing into a different rule. But same base equals same base. We just drop it off and take the insides. We don't have to do anything fancy. No switching anything around. We just solve the inside pieces. All right, starting where we left off, we just did 15 and 16, and that was same base equals same base. You take the inside pieces. I got a couple problems on 17 and 18. 18 has a couple of similar bases, but they're on the same side, so I got a problem. And 17 only has one base. So, I'm actually going to do something a little bit out of order. I'm going to do 20 first, because the really quick thing that you do on number 20 is how we solve 17 and 18. So 20 says rewrite each equation in exponential form, because we know a logarithm is just a different way to write an exponent. So the pieces of a logarithm, we have a base. Okay, this little chunk, the equal to part, that is the exponent. That is the exponent. So when we are using all these different things before, I said there was an easy way to remember how to switch it back and forth, because that's what we basically are doing. We're going to switch it back. Well, base in a logarithm is base in something that has an exponent too. So I have to have 225 to the 1/2 equals 15. And we know that's true. If we type that into our calculators, 225 to the 1/2 does pop out a 15. And so that's just, that's legitimately the answer. What is the same thing from 20 to, from the log to the exponential? They're the same thing, just a different way to write it. Well, here's the thing. Using that is how we have to solve 18 and 17. 17, the piece that we're looking for, that b to get by itself, it's inside a logarithm. And I have to do this little switch thing to get it outside of the logarithm. Because notice the 15 was inside and somehow we got it outside. That's why we have to switch it over. So, but first I have to get this log by itself. So I need to divide both sides by a negative 10, which that is pretty awesome because it's gone on the oops, sorry. It's gone on the left-hand side because you obviously divided by that, but on the right-hand side, it's still just a 0. So the piece I need is inside. In order to get it out, once the logarithm's by itself, we're going to do the switch. We're going to say, okay, 12 to the 0 power, that's hard to see, let me pick a different color, much better, equals negative 7b. So anything to the 0 power we know is 1, so this is really 1 equals negative 7b, and if I divide by negative 7, then b is negative 1/7. Shock. It works. Okay, so anytime you have a log by itself, there's no two logs, it's a log equal a number. When you have that, log equal a number, then you have to switch. You have to switch it over. And I know that's a lot of jumping around on this problem, but there's no other way I can get that b outside of the log unless I switch it back to an exponential. That, like I said, if I was taking this final, I would have that somewhere on my little cheat sheet, note sheet, is to say if log equals a number, I have to switch it over. I have to do that. And you'll see that when I post the picture of my key as well. You'll see my little notes on this problem. In 18, we're going to try it the same way, but I have too many bases to start out with. I have 2 on the same side. And we had just finished talking about combining them together. I would like to get it like 17, a log equal a number. And I can do that. I know that subtraction, if I want to smash these 2 logarithms together, I'm going to make it division. So I'm going to put x plus 1 over x equals 2. And now, even though it looks a little bit scarier than 17, I still can switch it over. I can do that. I'm going to say 8 squared equals all of this. 8 squared equals x plus 1 over x. Well, here's one thing that I know. I know that x squared is 64. So let's just change that. 8 squared is 64. And if I'm trying to get the x's by itself, I first have to get rid of this ridiculous fraction. And to do that, I got to multiply by the denominator. So I'm going to multiply both sides by x. And I get 64x equals x plus 1. Okay, I need to get the x's by itself, so we're going to move all of the x's to one side. I get 63x equals 1, and we're going to divide by 63. So it's another weird fraction, even crazier than the other one. I get 1/63 is my answer. So a little bit nuts, but it all works out. 17, I had log equal a number, and I had to switch it over. 18, well, we combined first, and then we did the switch. So that's why I wanted to do 15 and 16 separate. 15 and 16 are just easy. Same base equals same base. Drop them, pick the inside pieces. When you don't, when you have something like 17 and 18 where they're all on one side and you got to combine it and you only have one logarithm, then you have to switch it over. That's why I did 20 first. Okay, so we can see the different switches. Those are huge things that would be really helpful on this final to know, or maybe have on our cheat sheet, so if we had to look at it, we could do that. And that little switch comes in handy on lots of problems, even number 19. Now there's a lot of different ways we could find this. Evaluate each expression. You could absolutely just throw it onto your calculator. You could do that. If you know where that log base button is on your calculator, or if we did change of base, log of 36 over log of 6, you could get the right answer. You can also think about it like this. If we do the little switch, we're saying 6 to something is 36. 6 to a question mark is 36. Well, we know what that question mark is. How do I do that? That question mark is 2. And if you typed it in on your calculator, whether you could type it in just like it says, the log base 6, that's under the math button, or if you do change of base, any way you do it, you just get 6. So evaluating it, you got to figure out the answer. We can do the switch, use your calculator, however you want. Okay. 21, the problem that comes up next, is kind of the opposite of what 20 said. 20 said change the log into an exponent, or an exponential. So instead of log base 225 of blah, 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 all that stuff, we said, nope, 225 to this exponent is 15. Well, now, I want to switch it around. I want to take this 7 to the 0 equals 1. I want to write it as a logarithm. So first step, you got to write the word log. Duh. Okay? And we're going to do the switch as well. Base is still a base. Whether it's a base in an exponential or a base in a logarithm, we're going to switch it around. So this is saying log base 7 of 1 equals 0. And that's something that we have to notice. That 0 was the exponent in this problem. It's the equal to part over here. That's the same thing with 21. If we go back, if I look at 21, 225 to the 1/2 equals 15, the equal to part was the exponent. That's the same thing. They go back and forth. The equal to part was the exponent, that they match up, that we have to be able to do. If we can draw that little circle, this number comes first. There's your base of this equals this. We can go back and forth, make it work out. Okay? If you need to, if you want to make sure you're right, you could type log 7 of 1 into your calculator and make sure that it equals 0. You could type it in, you could try, and it would work out. Those are some little tips that we can think of, but doing the switch helps quite a bit. And these last two are finally towards the bottom of the log pages. We had factoring and foiling on the first page and polynomials. Now we had logs and exponentials and condensing and expanding. We got these last few, exponential equations. I have to solve the equations. And the pieces I'm looking for, the x and the n and all this stuff, are up in the exponent. But the great thing about it is 15 and 16 we decided were the easiest ones. We drop the bases, we take the inside pieces. I'm going to try to do that with this one. If I can get same base equals same base, like they both have to be a base 2 or they both have to be a base 5, then all I need to do is take the exponents. I can drop off everything else and just take the exponents. So if we look at these crazy numbers, 243 and 27, we have to write them as something that is similar. 27 is one that sticks out to me. I know that 27 is 3 cubed. So that really is, instead of 27 to the 1 minus 2x, how about 3 cubed to the 1 minus 2x? Well, if I try it and I test it out, 3 to the 5th is 243, something I can just figure out on my calculator. Okay? And it's also to the 2x. So our exponent rules, when you have numbers, powers to powers, we multiply. So this looks like 3 to the 10x equals 3 to the 3 minus 6x. Distribute that 3 to both pieces. And now we have this same base equals same base. If you get them to match, if 3 to this power is the same thing as 3 to this one, well, it's the powers that are equal. It's the powers. So we are going to solve for x. Much easier equation now. Okay, I'm going to, let's see, we'll move over the, oh, sorry, that should be a 10x. I left something off. I was thinking something was wrong with this, 10x. My apologies. So we're going to move over the negative 6x. Let's add it to the other side. So we get 16x equals 3. Looks like x is going to be another crazy fraction. No panicking, we can deal with fractions. X equals 3/16. That's what it's going to work. So just like 15 and 16, we drop the bases, we keep the other parts. If we can get the bases to match up, I'm going to drop them and I'm going to keep the exponents. So we're going to keep the same rules for 23. The great thing about it is I already have a really small base. 2 to the 2n, that's really small. And I can write 16 as a base 2. I know that's 2 to the 4th. Okay? So instead of 16 to the n minus 1, 2 to the 4th to the n minus 1. We can distribute that 4 to both pieces, so we get 2 to the 2n equals 2 to the 4n minus 4. Same bases, both sides. We're going to drop them, and we're going to take just the exponents. Okay, so we got it. We can do this. Let's see. I'm going to move the n's to one side. How about we subtract 4n over? I get negative 2n equals negative 4. If I divide both sides by a negative 2, it comes out positive. We got a positive 2. Both sides, this is going to work. So on problems 15 and 16, 22 and 23, if we can get the bases to be the same, we get the bases, we drop them off, and we take those exponents. Alrighty, so after logarithms, next came solving systems of equations. If I put lots of equations together, if I can find a point, or if there's three of them, if I can find a triple, maybe the place in 3D space where they all meet. And one way we did that, if it looked a little crazy, kind of like 24 and 25, was a matrix. And we could do that on our calculators when we went to the matrix menu. It's on the left-hand side of your calculator. And the first thing we have to do when we get there is we have to go and edit the matrix. Now, both of these matrices that we would use are what we call 3 by 4, because we have three equations with four coefficients, the r, the s, the t, and then the equal to part, what they equal to. So notice my before matrix the coefficients look a little bit different than what it started with, because we have to move everything to the left. Everything has to go to the left. So really, this second equation should be r plus 2s plus 6t equals 24. That's why that second line is all positive. There's a couple zeros, notice, because this one doesn't have an r and the first one doesn't have an s, so we toss in some placeholders. Okay, but once we get it all set up and it's all good to go, then we do what it says here, is to reduce it all the way down. The command was RREF, and I put matrix A. You can do whatever letter your matrix came in. And once we do that, the after matrix is, pause for a second, this. And notice the thing we wanted to look for that we hope showed up was this diagonal of 1s, because that meant that we had 1R was 6, 1S was 6, and T was 1. So we had this ordered triple of 6, 6, 1. That was our answer at the very, very back. Okay, that's going to be the same thing for 25. My before matrix looks like this. The first one's missing r's and t's. The second equation, well, it's all good. It's on the left-hand side, and so is the bottom one. It just doesn't have any s's, so that's why we have some zeros. So we type it all in. We go re-edit our matrix. We do RREF. And out pops the after matrix with the answer, -2, -2, 1. That would be our ordered triple. It works if you only have two equations. Instead of a 3 by 4, you would have a 2 by 3. But we're looking for the diagonal of 1s, and whatever is behind it, that last column, is our answer. And matrices are just one way that we could solve. Another way we could solve by graphing. If we graph them and obviously saw where they actually crossed. So in 26, that's what we're going to do. I have a y equals line, and y equals are horizontal at that number. Maybe you want to put that somewhere on a cheat sheet. X equals are vertical. They are vertical lines. I'm doing multicolor so we see it. Y equals are horizontal. X equals are vertical. So this line, y equals 1, positive 1, all the way across. It's pretty dang good for an iPad. And this second line, we got to be careful for. This number back here is my y-intercept, where it's going to start on the y. There should cross up at the y-axis. My slope is -2, so that means instead of going up and to the right, up and over, we're going down and over. So down 2 over 1. Down 2 over 1. We kind of see where they're going to cross right there. Down 2 over 1. Down 2 over 1, down 2 over, and so we're going to make it cross, and we see exactly where they meet, what point that they both share. It looks like 2, 1 is their point that they share in common. Now, obviously, because of time constraints, your test is multiple choice, so you won't be graphing it, but your answer choices will be 4 graphs, and you have to pick out which one is correct. So we have to know how to graph these lines. What should we be looking for? You know, negative slopes go downhill. Y equals lines are horizontal, so don't pick the one that has a vertical line. Things like that. And kind of goes along with graphing where inequalities, like number 27. The thing with inequalities you have to remember is there always should be some shading. And we have to decide, can we have a solid line or a dashed line? Well, both of these are going to be, oh, that's ugly. Undo. Both of these are going to be dashed because they do not have the equal to bar underneath it. And I purposely made these fractions because on tests and quizzes that we had, we kind of struggled with some graphing fraction slope. So we're going to make sure we got this. So the top line looks like my y-intercept is a -3, so I'm going to put a point down at -3. And this looks, we know how to do up 1 over 2, but it has to go backwards. So we can go up 1, but we have to go back 2, up 1, back 2, or down and over, down and over. We have to make sure it goes downhill. That's the thing you got to look for. Not every line is positive. We can't do it that way. And this is a dashed line, so we're going to connect the dots with dashes. Our second line, it starts at -1, so still below. And then this one has a positive 1/2 slope. So we are going to go up and to the right and up and to the right. Up 1 and over 2. Up 1 and over 2. It's always, always, always rise over run. Okay, do not get that confused, but it's always going to be rise over run. We got our dashed line. So we've done both of the lines. They're both dashed. Now we just have to remember to shade. And it says less than on both of these. Less than is below. I'm shading underneath. I need to go under that line, smaller than that line. And under both is this little section down here. This one up here, that's greater than both. We don't want that one. These two would be, if the signs were different, we just have to decide which one is above, which one is below, but we don't want that one either. We want this one. It's below both of them. So those are some things you got to check for on inequalities. Again, it's multiple choice. So you won't necessarily be graphing them, but you have to be able to pick out the graph. It'll be, A, B, C, and D. Your choices are graphs, and you got to match them up. That one of them may look exactly the same, but the shading's in the wrong spot. Or they look exactly the same, except one has a solid line and not double dashed. I don't know. It's up to you to decide which one it is. Maybe some tips on your cheat sheet will help you out with these problems. All right, 28 through, let me see here, 33. This is some of our most recent stuff, this sequences and series. I kind of call this AKA the calculator section. It's basically formulas, and you just have to put them in the correct spots to get the right answers to pop out. We had different types, arithmetic, geometric. Arithmetic we added to get to the next number. Geometric we multiplied. And so there were all of these different little teeny tiny pieces that we had to know. N was how many terms. D, common difference, what were you adding every time. R, what were you multiplying by each time. A sub 1 is your first term. All those different things. So when we see these, really we just got to make sure that we put some parentheses in the right spot. Like 28. I need to find, it says A sub 34, the 34th term of this sequence that started at 0, and it looks like I added -20 every time. So if I need to find the 34th term, and know it started at 0, and then that means I must have added, I'm going to write over this, 34 minus 1, -20s. I subtracted 20 33 times. So the 34th term is really 33 times -20. We type it into our calculator. Out pops -660. That's all we need. It's a straight calculator problem. We make sure we have all the formulas that we need. They should be there on the test. They're typed in. No need to waste space on your cheat sheet for that. And number 29 is going to work the same way. I have a formula. I need a certain term. It tells me in my problem which term I need. I need the 8th term. This is geometric. I started on a 4. And every single time I multiplied by a -3. So I had 8. If I want the 8th term, that must mean I raise it to the 7th power. I multiplied by -3 7 times. Again, type it just like that into your calculator. Do not do, this is a no-no. Do not do this. -12 to the 7th. Nope. You cannot multiply before exponents. Order of operations says exponents before parentheses, before multiplying. So if we type this in just like we see it, the correct answer of -8,748 should come out to get our 8th term. So we type it in just like we see it. Do not multiply the two numbers before you raise it to the exponent. Number 30, it changes a little bit from sequences to series. Series just means you have to add some things up. You're finding sums. We can tell that also because the formulas both now have S's instead of A's at the beginning. So I want the sum. It's arithmetic. I'm adding something every time. The first term was 16. Whatever the last term is 76, and it looks like I had 7 terms. So really it's the first term plus the 7th term, because I'm adding them all together. So if I have 7 divided by 2 times the first term plus the last term. And one thing maybe I would do before you type it into your calculator is to fix that fraction up front. 7 divided by 2 is 3.5. Sorry, my phone's going off. My mom is texting me. How cute. Anyways, but I'm going to simplify that number in front. That just makes it a little bit easier to type into your calculator. So I want 3.5 parentheses 16 plus 76. The sum of those first 7 terms is 322. So difference between 28, 29, and 30. 28 and 29 are certain terms. 30 and 31 are sums. And, oh, I didn't mean to zoom in. Sorry, let me fix that. There we go. So now, there it is. That's what I meant to do. 31, crazy, crazy formula. Definitely a calculator problem. If your calculator does the fancy fraction where if you do that whole alpha y equals, I would be using that. If it doesn't have that, I would input the top and then divide by and put the bottom part in parentheses. But we're just going to plug it in the numbers that we need. I'm looking geometric series this time, so geometric sum. The first term is 3. It looks like I was multiplying by 2 every time, and I did it for 9 terms. That's how many terms I want. So if I type this in, like I said, maybe if you're doing it step by step, plug in the top part exactly like you see it, and then do divide by, what, a -1? That's what 1 minus 2 would be. You could do it like that just to make sure you get the correct answer. The correct answer should be, if you're just checking, you can always pause it and do it yourself and then check, is 1,533. 32 and 33 are a different way to talk about sums in series, where we had summation notation or sigma notation. All that this meant was it told you which term to start with, it told you which term to stop on, and then it told you your rule, what you're plugging in every single time. So I have to start with the first term, and then find the first and the second, the third, the fourth, the fifth, and then add them all up. You have to add them all up. It's a must on 32 and 33. So let's see, the first term, if I plug in a 1, I get 2 times 1 minus 5. Let's see, that's a -3. Second term, plug in a 2, I get a -1. Third term, I get a +1. Fourth term, I get a +3. Fifth term, and final term that I'm plugging in, I get a 5. So this is great that I know all the terms, but I have to add them all together. Well, this is kind of convenient, because if I take and add all of these together, you may notice that some are opposites, like 3 plus -3, 1 plus -1. So really my answer is 5. Adding all of those terms up, the sum is 5. And we're going to do the same thing for 33. I'm going to find the 4 terms using this rule. My first term would be, let's see, it looks like -3 to the 1 minus 1. That's -3 to the 0 power. Well, anything to the 0 power is 1. My next term, if I plug in a 2, that means I get -3 to the first. Well, anything to the first is itself, so -3. My third term is going to come out to be -3 squared. That's a +9. Better be a +9 because that -3 is in parentheses. And my fourth term is going to come out to be -3 to the 3 power cubed to the third power, which is -27. And now I'm going to add all of these up. Plus, plus, plus. It should equal -20 when we're finished. So if you see the word series, sum, the sigma sign, that means you have to add them up at the end. You got to. It's not an option. And our final 2 that we're going to wrap up this video with are our 2 circles. Circles, again, you won't have to graph any. We're practicing graphing, so we know what to look for. You will have to pick it out multiple choice. But for circles, you need 2 things, the center and the radius. So we have x squared, y squared, radius squared. So the radius is the square root of 1, which is just 1. So this is really teeny tiny. The center will be positive 4, positive 1, because it is always opposite of what it looks like inside your parentheses. So at positive 4, positive 1, it looks like we have the center right about there. And if the radius is only 1, this is a really teeny tiny circle right there. We got that. We know the few things to look at. Centers don't have a lot of stuff. But one thing we have to be careful with is what if we have to complete the square? And we can do that. First step I'm going to do is I'm going to flip-flop these two so I get the x's and y's next to each other. And I also move the -3 to the other side. So when we complete the square, remember this was looking for perfect numbers. We wanted to see, oh, that's kind of hard to see. There we go. What were the perfect numbers to add not only to the left-hand side, but also add it back to the right-hand side as well. And the way we did that, half it, square it, add it. I take that middle number, -6, and I'm going to half it. I get -3. To square it, I get a positive 9. So positive 9 is one of the perfect numbers that I have to add in to the other side. The second perfect number will come from the y. So when I take the 4 and I half it and square it, well, that just becomes a 4 again. So that works. Oh, not a 9. Sorry, 4. And I'm going to add a 4 to both sides. Now the reason why we do this is that if I factor this, becomes a perfect thing. Two numbers that multiply to negative or positive 9 that add to -6, double -3s, which means I can write this as x minus 3 squared. Same thing with the y's. Two numbers that multiply to a positive 4 that add to a positive 4, double positive 2s. But I can shorthand that to say, how about we just do y plus 2 squared? And then when I add up all of this on the other side, 9 plus 4 minus, or plus a -3, I get 10. So now it's in what we call vertex form. It's the nice, neat form because I can see that my center will be positive 3, -2. Remember, we go opposite. My radius will be the square root of 10. And yeah, this kind of stinks because 10 is not a perfect square. No biggie. We're going to go with our best shot. Decimal-wise, it's like a 3.2. So we're going to go out 3.2 either side. So our center is at 3, -2. And we're going to go out 3.2 units on either side. So 3 and just a little bit past either direction. 1, 2, 3, and a little bit past. And we connect the dots. I will be nice and make sure it's a perfect square at the end. But completing the square, get the x's and y's together, half it, square it, add it, so you can write it in beautiful vertex form. And to continue with our conic sections, we're going to look at hyperbolas next. We know it's a hyperbola if we just look at the equation. It's got the minus sign in it. So I know it's a hyperbola. It's broken apart. Okay? And so we need to identify a few pieces from this. It says state the center, so we got to have that. The major axis, the minor axis, and then we got to sketch the graph. And the other thing we have to think about with hyperbola is the way it opens, because it depends on which letter comes first, which axis does it open, just like the y-axis, does it open horizontal like the x-axis, that's what we have to decide. So a few things. We're going to get the center, kind of like with the circle, how we get it, what's inside the parentheses with the x and the y, and there is a whole lot of nothing inside the parentheses with the x and the y, so the center must be 0, 0. We can throw that on our graph. Now to decide the major and minor axis, we have to take the square roots of the pieces underneath and then double them. This is, 9 is going to be our a squared because a squared is always the bigger number. 4 is b squared. So if we just want a, just half, that's 3. And if we want b, just half of the major minor axis, that would be 2. We take the square roots of them. So the full length of the major axis is 6 units all the way across. The minor axis is 4 units all the way across. These two give us half. These two doubles it. That's what we have to take from it. Now there's a few things we need. The 9 was underneath the y, meaning the major axis has to go up and down. The smaller number, the 4, was underneath the x, So the minor axis is going to go left to right, just like the x-axis. And since the y is first, this must open up and down. It has to open up and down because the y is the positive one. That's what we're looking at. So here's how we can do this. Let's see, if we need to go 6 units as the major axis from one side to another, that means half in one direction, half in the other. So I have to go 3 up and 3 down. I also have to go 2 to the left and 2 to the right of my center because the full distance is 6 all the way across for the major and 4 all the way across for the minor. Now I'm going to make a rectangle around these little points because we know there are some guidelines that the hyperbola has to follow. We can't just randomly draw it on our page. We kind of know there's some asymptotes, there's some boundaries. But as long as we kind of can make a little X around it, then we're okay. And to put our graph, I'll do it in blue, the actual hyperbola, it's got to open up and down, so it's got to bottom out and top out right at those vertices where it touch on that little rectangle. And so we have hyperbola with a center at 0, 0, a full major axis of 6 units because the A is only 3, that little half distance, there's A. The B is 2, so all the way across is going to be 4 units, and it opens up, down because the Y is first. Since these are multiple choice, those are all the little bits and pieces we got to look for to know, okay, major axis is up and down just like the Y, minor axis is the X. Those are the little pieces, maybe some tidbits and help tricks that we write on our cheat sheet. So the ellipse is another shape that we have. It looks similar to the formula looks similar to the hyperbola, but it's a plus sign instead of a minus sign because the ellipse is connected. It's not broken apart, but all of the pieces are exactly the same that we need to find. I still need a center. I need the major axis length. I need the minor axis length. I just don't care about the direction of opening this time because ellipses, well, they don't open. They either stand up tall or they lay down kind of like a football laying there. So we're going to decide the center first. It looks like there's nothing with the X, but there is a 1 inside with the Y, and it looks like a -1 inside, so we always take the opposite, so it's going to be a +1. So I got my center is at 0, 1, so no left or right movement, but I did go up 1. There we go. Let's see. Bigger number, A squared, this time is under the X instead of the Y. So if I take a square root to get half of the distance, it looks like A is 7, B is 4. So when I come over here to find the lengths of the full major, I have to double it. 14 units for the major axis. Looks like that number was underneath the X, so it's got to go left and right. Bigger number underneath the X. Okay. Smaller number, the B, the 16 at B squared, it was underneath the Y. So my major axis is going to be up and down like the y-axis, and it's going to be 8 units all the way across. It's double the 4. So we go square root to get these, and then I double it to get the major and minor axes. So let's see, if we need to go smaller number, the B, the 16 at B squared, it was underneath the Y. So my major axis is going to be up and down like the y-axis, and it's going to be 8 units all the way across. It's double the 4. So we go square root to get these, and then I double it to get the major and minor axes. So let's see, if we need to go 7 units in either direction, left or right for the major axis, that means 7 left, 7 right, and then it's 8 units all the way across, 4 up and 4 down. I got to go up 4 and down 4. And then it's an ellipse. It's not a hyperbola. Hyperbolas, we'd have to draw a box around these and flip it out, break it apart. But an ellipse, we're just going to connect as best as we can to see it. Okay, bigger number was underneath the X. Notice that it is fatter. It's wider than it is tall. It has more length in the X direction than in the Y direction. That's how we can kind of see how it goes. Multiple choice, match it all up, pick the picture that goes with the equation. Alright, and for 38 and 39, those are first conic section. It's the last one that we're talking about on the videos, but it's the parabola. Parabolas we talked about many times this semester. We talked about with conic sections, we did it with quadratics, and we factored. But there's only a couple things we need to identify with parabolas. That is the vertex and the direction of opening. And so vertex form is the one that had all the parentheses. This one that we have on 38 is kind of that way. There's nothing paired with the x. So it really could look like this, x minus 0 squared minus 5. So I can do a little, finagling, putting a 0 in a pretty convenient spot to realize, oh, that is in vertex form, that we can find that. So vertex-wise, the vertex, I'm going to take the point, looks like 0, negative 5. Remember that minus 5 is on the outside, so this is the opposite number, but it's just a 0. And it is the literal number. Literal. Can't spell. Too many A's. It's the literal number that we put there. So we're going to go down here and put our point at 0, negative 5. That's what our vertex says. Let's see, now we need to talk about the direction of opening. Well, direction of opening for y equals parabolas, these are the normal ones. These are either up and down, and it's going to depend on if that number in front is negative or positive. So I have a positive number. And a positive number, a positive y equals, means it's going to open up. It will open up. And if it was negative, it would open down. It turns everything upside down. And here's a pretty convenient way of how to figure out, well, I don't want to have to plug in points. How do I do this? This number in front is a 2. So we're going to go from our vertex, and if we go over 1, our next point is going to be up 2 on either spot. It just kind of makes the parabola a little steeper. Numbers in front usually are like slopes, or they were the amplitude on sine, cosine, and tangents and all that stuff that made it steeper or it made it flatter. That's what it's going to do. So if that number in front was like a 7, I would go out 1 and up 7 spots. That's what we would look for. But when we jump over to 39, a little bit different. Put a big star, something to draw your attention that this is an x equals parabola. These are the ones that are a little bit different because x equals parabolas will either open left or they will either open to the right. They are the laying down parabolas. They're the ones that open differently. But we're going to try still get the same pieces. We need a vertex, we need a direction of opening. So here's the thing. If we look at the vertex, this time the number that's inside, it's looking like a y because it's paired up with the y. And now this number back here, this negative 3, because it's on the outside, so I take it for what it's worth, I don't change the sign, is actually the x. It's the x value, because this positive 2 that's inside, that's really a negative 2, that's the y. So when I have x equals parabolas, the vertex gets switched. It switches its spots. So negative 3, negative 2, all right, we're going over here, got it. And direction of opening, well, this is negative, but it's not going to open down. X equals parabolas go left, right, and if I need negative, that means I need to open towards all the negative numbers, and that would be to the left. Those are all of those negative numbers. That's where we have to look for. So if we go to the left, it looks like it's just a 1 in front. It's not a 2 or a 7 or anything. The 2 on 38, remember, we went up 2 points from our vertex, okay? So this one's just a 1. That means I'm only going to go 1 up, or 1 to the left of my vertex for this one, and I have to make it open to the left. So those are all the conic sections. Those are the things that we have to find. Centers and vertices, directions of opening, radius, major, minor, all those little tips, little bitty things that you don't have to find it to graph it, but you have to know what they are to look at all of the multiple choice answers and answer all those questions. All right, and another type of graph that we dealt with were these graphs called rational functions. Rational fraction ratios, that's what we're looking for. These were the broken ones. They had asymptotes, and they had lots of different stuff we found. They had things like vertical asymptotes, horizontal asymptotes, holes in the graph, all these pieces that we had to find that we could tell just by looking at the equation. We could tell that. And there's a certain order that we kind of picked out all these different pieces in. It just kind of helped us out. And so here are the rules. This is probably my number one thing if I was going to be taking this test that I would write on my cheat sheet, would be the rules for these little guys. Because, yes, there's only one graph on your review, but 41, 42, and 43, you got to know the rules to be able to make up an equation, okay? So, I kind of jotted down the rules, so you may want to take a moment and kind of pause the video, jot them down, and then you can listen to me, ramble on again. But I'm going to go ahead and go. For horizontal asymptotes, we look at the degree of the top and bottom, the numerator and denominator. Degree, highest exponent. That's what we're looking at. Okay? There's obviously a few things that can happen. They can be equal, like the bottom one says. The top one can be greater, or the bottom one can be greater. Just depends. Okay? If the top is less than, the bottom is the bigger piece, then we have a horizontal asymptote at y equals 0. That's the x-axis. If the top is greater, we don't have one at all. That's a none. Okay, and here's the big one. If they're equal to each other, it's a y equals line, but I'm going to put LC over L, that looks like two L's, LC over LC. Leading coefficient over the leading coefficient. We jump to the numbers in front if they match, if they really do match. And so if we check out our function, the degree of the top, well, it's kind of like a 0 because there's no x, and the bottom, the highest exponent I have is a 1. So obviously the bottom is a lot bigger, not a lot, just by 1. It's bigger than the top. So I have this rule right here, that my horizontal asymptote occurs at the x-axis at y equals 0. So we're going to draw that line in. Got it. So we checked off that one. Another thing that we had to look for, what if there was a legit hole in the graph? Like it just had a spot taken out. It looks like someone just pulled a point right off the graph and just left it blank. That happened if there was a factor that was the same on top and bottom, like an x plus 2 and an x plus 2. X minus 7 over x minus 7. An x over an x. Well, one thing, I can't do this. Oh, look, there's a factor. No. You can't cross off the 2's. Because this 2 on the bottom, it's attached to that x right here. I would need another, like, x minus 2 to be able to cross something off on top. And I don't have that. So for our purposes, I don't have a hole in this graph. We said we did have a horizontal asymptote at y equals 0. There are no holes in this graph. It's a continuous graph as much as it can be. So the only other thing we could have is a vertical asymptote, the worst kind ever. These are the undefined spots, things that when you plug it into your calculator, it's going to say error because it doesn't exist. And the way we find that is whatever factors are left on the bottom, we set them equal to 0. So it looks like I have this x minus 2 that's still left on bottom. And that piece cannot be 0. There's a number that if I plug it in, it's going to give me havoc with fractions. And that would be the positive 2. We see that. So I do have a vertical asymptote at x equals 2. Okay? And we can graph that. I'll put all of our things up at the top. X equals 2. That's a vertical line. Remember we've already discussed x equals are vertical, y equals are horizontal. Well, this is great, but we really haven't graphed anything yet. We've graphed where it can't be, what it can't touch. So here's how we do it. Okay? What we're going to do is we're going to plug in some points to help us out. Now, I think you can plug in any x values you possibly want. But we at least need one on either side of the vertical asymptote. I think the easiest numbers to plug in would be the 1 and a 3. The two numbers that are right on either side of that asymptote. Because if we take this and say, okay, we're going to plug in a 1 and a 2 to this little teeny tiny x up here. Got it? So we're going to say 1, how about 2 over 1 minus 2? Well, if you plug that into your calculator, out pops a negative 2. Okay, 2 over a negative 1, yeah. If we plug in a 3, looks like I get 2 over 3 minus 2. I think the easiest numbers to plug in would be the 1 and a 3. The two numbers that are right on either side of that asymptote. Because if we take this and say, okay, we're going to plug in a 1 and a 2 to this little teeny tiny x up here. Got it? So we're going to say 1, how about 2 over 1 minus 2? Well, if you plug that into your calculator, out pops a negative 2. Okay, 2 over a negative 1, yeah. If we plug in a 3, looks like I get 2 over 3 minus 2, so 2 over 1, I get a positive 1. Great, I have 1 point, 3 positive 2, I got a point right here. I got 1 negative 2, I got a point down here, and that's really all I need, because if I start at the point that's on the right, if I keep going as far to the right as I possibly can, all this is going to do is drag it close to that asymptote. Same thing if I go to the left, it's just going to shoot straight up. And so we can kind of do the same thing with the bottom piece. We just take the shape of whatever section it's in. That is the rational function. It's broken. There's a problem at x equals 2, and then we have that horizontal asymptote at y equals 0. All of those little rules and tidbits are probably the best to pick out. If you get to the multiple choice and you got all the pieces, but some of the graphs still look the same, that's when you got to go for the points. That's when you got to say, okay, I can plug in a few points. Which one do the points match up the best? Got to know the rules: horizontal, holes, vertical asymptotes, and you'll be great. 41 through 43, you can have tons of examples. When I post my key, if I just take a picture of it, I did 3 examples on each. I'll do a couple here, but it really is up to you. You have to come up with a rational function that makes this work. On the test, it's going to be, say, hey, pick out the one that has a hole in the graph. Okay, we could do that. So here's what we have to decide. We need to look to see, we need to make up a function that has a hole in the graph. Well, we just said that holes are when you have a factor the same that's top and bottom. So here is one pretty easy example. How about we do this? X over this. Ta-da! It has a hole because there's an x here and there's an x here. That would work. We could make something that looked like this. How about x plus 7 times x plus 2 over x plus 2. Yep, it's got a hole in the graph. The plus 2's cancel out. Or we could try this one. Here's the last example. How about this? X squared plus 2x plus 1. Well, it doesn't look like it. How do you know? Well, you factor the bottom piece. You get x plus 1, and one of those would cancel out with the top one. So as long as whatever thing you make up has a chunk, has a factor that is the same on top and bottom, then it works. 42, something that has a vertical asymptote but no horizontal asymptote. Something that we have to check on. A vertical asymptote, there is something that's left in the bottom. Obviously, there's something that's left in the bottom that's going to give us a problem. But no horizontal asymptote. That means that the degree on top must be greater than the degree on bottom. So the top has to be greater than the bottom. These are some things that we have to check out for. So here's a couple of examples. How about x cubed plus 2 over x plus 7. Okay? The degree on top is bigger than the degree on bottom. And there's something left over in the bottom. Okay? I would have a vertical asymptote at x equals negative 7. Okay, that would work. And let's see, here's another one. I'll give you one more. How about, well, that one we talked about, the x squared where the x plus 1's canceled out just a second ago. What if you turn it upside down? Okay. It would have something left on bottom. Degree on top is bigger. You could change it up and make the exponents crazy. Say I'm going to put x squared plus x plus 17. Whatever it is. As long as there's something left on bottom and the highest degree on top is bigger than the highest degree on bottom, then this works out. And this last thing that we have to decide, I need you to write a function that has a vertical asymptote at x equals 3. Got it. Well, here's the thing. If you have to have one at x equals 3, that means that the factor that made you get the x equals 3 was if I bumped this 3 back to the other side, if I subtracted it back over. So we need something that has an x minus 3 in the denominator. How about this? Pretty easy one. Done. Got it. Okay, it's pretty easy. Let's see, we could do something to make it fancy. We could say, put a lot of factors up top, plus 1, and x minus 3, and then an x by itself. As long as one of your factors is this, x minus 3, you can put anything else you want. The x minus 3 has to be in bottom, though. It's a problem. It doesn't say that's the only vertical asymptote. It just says there is one. Those are the things that we got to look for. So knowing all of those rules for the graph come in handy for these problems as well. Alright, so we got to the i's on the back page, finally. Now for the most part, this work with the i's is similar if these i's were x's. The biggest rule, if we get an I squared to pop up, you got to change it to a negative 1. So I'm going to do these out of order. I think the easiest one first is 45. All it is saying is adding these two numbers together. This is pretty basic. I take the number parts and add the number parts. So 8 plus a negative 3, that gives me 5. And the i's plus the i's. Negative 8 plus one more I, that's negative 7i, and I'm done. 5 minus 7i. That's pretty basic. Okay, 46. It looks like when you get one little piece on the outside of all these other terms, it looks like we got to distribute, and that's exactly what we're going to do. So I need to distribute the 7i to the two pieces here, so I get 14i plus 42i squared minus, minus 6 plus 4i squared. So we have all of these little pieces, and now we just have to fix them. And I have to fix this. That shouldn't be a 4i squared. That should just be a 4i. I messed that one up. Sorry. I'm miscounting all of those i's. Here's what we can do. First thing, looks like we have 14i plus 4 of them at the back. So we have 18i total. And this little 1 or I squared, we're going to change this out to be a negative 1. So that's really like 42 times a negative 1. So with all of those 18 i's, I also have minus 42 minus 6. So we're going to combine these two numbers. And usually, if we're getting technical, the number part is in the front. So negative 42 minus 6 more is negative 48 plus 18i. We got all of those pieces. If you had them backwards, you would know because your answer would be exactly backwards in the multiple choice. It's okay. It's not a big deal if you don't put the number part first. That's just math. It's technically prettier math. 44, what I do not want you to do is distribute that square. We don't do that because when we see something, two terms that have a square on the outside, we really know that means you have to write it twice and you multiply. This is a FOIL problem. So let's see. First, outside, inside, last. We get 49 plus 56i plus another 56i plus 64i squared. So here's a few things we can fix. We can add the 56 i's in the middle. I'm going to swap this out. An I squared is really a negative 1, which turns this to a negative 64. So that's 49 minus 64. I get negative 15. And 56 plus 56, I have 112 i's right there in the middle. So adding and subtracting. Distributing, we just combine like terms. When you see multiplying, it's just like foiling, and we combine like terms. We just have to swap out the negative 1s for the I squares. The difference comes in 47. So this is kind of like dividing, but really dividing, simplifying just means I need to get the i's out of the denominator. They can't be there. So the way we do this is we're going to multiply by the conjugate of the bottom. Sounds really fancy, not super hard. Let me pick a different marker. There we go. The conjugate of the bottom, all that means is you got to change the sign that's in the middle. Okay, if it says negative 4 minus 5i, then I'm going to multiply by negative 4 plus 5i. Okay, if it said the conjugate of, this little piece would be 3 plus 2i. Not that we need it, but if that's what we were looking for, then we could do that. So we're going to multiply top and bottom by that. The top part looks like we're going to be distributing that 6i over. So I will get negative 24i plus 30i squared. And if I FOIL the bottom pieces, then I get positive 16 minus 20i plus 20i minus 25i squared. So we got to fix some few things. It looks terrible. I know we're trying to get it out of the bottom. We just made it worse. Here's how we can fix it. Both of these I squares are going to become negative 1s. The bottom part, both of these i's are out of there. So let's jump down to the bottom. Ignore the probability that we're getting ready to do. This positive 30 times a negative 1. I get a negative 30 minus 24i up top. Okay. It looks like I'm going to have 16 and now plus 25 because I had negative times a negative. So 16 plus 25 gives me 41. Nope, not 4i, 41. And now it's perfect. The i's are out of the bottom. Multiplying by the conjugate, that's how we're going to flip it out of there. We distribute, we FOIL, we can change all the I squares, but the conjugate's the new part for that one. So we simplify. Everything is pretty similar to normal math, except the conjugate part, and I squared equals negative 1. You got to change it. And we're down to the final 3 problems, the best stuff, probability. And we're talking about a single die being rolled. So we know there's only a few options, a 1, 2, 3, or a 4, 5, 6. Those are it. So probability, what you want over the total. We talked about desired outcomes over the total outcomes. I'm running out of room, wrote too big. All of those. So each one of these is going to start with a total of 6 because there are 6 outcomes total. So here's what we're looking for. Find the probability of rolling an even number. Okay? Even number, a 2, a 4, or a 6. So it looks like the probability of that is 3 numbers out of the 6 total numbers. The probability is 1/2. Bing, bang, boom, you got it done. Not super hard. Let's try this one. Probability of rolling a number that's less than 3. It doesn't say equal to 3, so I can't pick the 3. So that would be the 1 or the 2. So desired outcomes over total outcomes. Desired outcomes, there's 2 of them, over the total 6 outcomes. And then I have a 1/3 chance of rolling something that is less than a 3. Okay? And the last one, we like probability. The probability of not rolling a 1. I do not want a 1. Do not want it. So that means I could roll a 2, a 3, a 4, a 5, or a 6. All of those are not 1. That's what we're looking for. So there are 5 ways to not roll a 1 out of the 6 total. Not much I can do to simplify that one. It's going to stay. So probability, those are the ones that you guys are great working on in class. We liked them. They were fun. What you want over the total. So we finished all of the review up. So things maybe you want to do. If you've put stars next to certain problems that maybe gave you some trouble, go back, rewatch them, see how we did it. Maybe if you've been putting stars next to things that you think should go on a cheat sheet, now is the time to go back and kind of fill it all in. Put some tips down. Maybe write a couple examples of what a conjugate is. Maybe write the conics rules, write the rational functions, the rules, the horizontal, the vertical, the wholes, all of that stuff. Writing synthetic division or the types of factoring or calculator tips or really big thing, log tips, how to solve log equations. All of those things, just take the time, make it nice, make it neat, make it legible so you can see it and you'll do great on your final on Thursday or Friday. It's been a great year, guys, and I wish you the best on your final. Be great.